All right, calculus students, we're here doing our second problem of fundamental theorem of calculus, and we have g of x as being defined as negative x plus the integral from 0 to x of f t dt. So you got to be real careful if they decide to define g of x with an extra little piece out here. That's going to be important in some of our questions. So we're here to find g of 4, g of 6, and g of 14. So let's go ahead and get started here. We're going to have g of 4. Well, g of 4 doesn't means exactly what it meant back in Algebra 1. Just take 4 and stick it in for all the x's. So I'm going to get negative 4 plus the integral from 0 to 4 for f of t dt. So what we want to do here is we want to measure the area under this curve from 0 to 4. Well, from 0 to 1 and 1 to 2, those end up being the exact same area, but one's positive and the other area is positive, but it's below the x-axis, so we'll call minus. So those actually cancel each other out. So the value of the integral, right, from 0 to 4 would just be this triangular area right here, and that's going to be 1/2 base times height, which we end up with a negative 2. So negative 2 ends up being the integral value, but we do get a value then of g of 4 to be negative 6. So there's my first answer. G of 6 is done similarly. Here we'll start as g of 6. G of 6 is going to be found by putting 6 in for the x. So I do get negative 6 plus the integral from 0 to 6 for the function f of t dt. Now, by looking at this, we can start off by saying we do have negative 6 for sure. And then I'm going to break this down from 0 to 4 first, and then go from 4 to 6. So the integral from 0 to 4, which we've already calculated to be negative 2. And then we're going to add to that the value from 4 to 6 to finish it off. So we have negative 6 minus 2. And then we look up at the picture from 4 to 6. We're talking about this triangle, which is the same size as the triangle below here. So it does also have an area of 2. So I guess the 2's we can say they cancel, but we have negative 6 as the final answer again. All right, now we have g of 14 to find. G of 14, similarly, we're going to have negative 14 because my function is defined as negative x plus the integral from 0 to 14 for the function f of t dt. And if you look at this kind of closely, let's go back and look at the graph here. I'm going to erase some of this. So we have from 0 to 14, we have this is a plus, but this is a minus. Those match. This is a minus, but this is a plus. They're the same size. So technically, we could just find the value of the integral from 6 to 14. So we're going to say this is going to be equal to negative 14 plus the integral value from 6 to 14. Probably just easier to do it that way. Of f of t dt. Okay, and it's all going to be positive since it's all above the x-axis, and we're measuring left to right. Okay, so here we have a 4, area 4. Here we have, I guess, an area of 2, and this is a semicircle with a radius of 2, so this ends up being 2 pi. So we have 6 plus 2 pi. So when I take 6 plus 2 pi, 6 plus 2 pi, and I add it to my, I guess, my negative 14, right, that I had from here, I get a final value of g of 14 to be 2 pi minus 8. Make sure you can read that. 2 pi minus 8. All right, now we're here finding the derivative. Now we have to make sure that when we derive this function here, we don't automatically assume that g prime equals f of x. That is usually what happens when you're teaching it. However, g of x is not defined as just the integral. It has this extra negative x, so it's going to be important. So when we derive g, we'll do it one time. We're going to get g prime of x is going to equal, and we're going to derive this negative x here. We get negative 1, and then we're going to say plus, and then when we derive the integral, fundamental theorem gives me then just f of x. So we're finding, pretty straightforward, we're finding g prime 2. Right? G prime 2 is equal to, well, these are all going to start off negative 1 plus a function value. So we're going to have, I guess, 4 of them. So we're going to find g prime 4. We're also going to find g prime 10. And then g prime of 12. And all of these, right, all of these will have a negative 1 to start it, because it's part of the rule. It's negative 1 plus the function value. So it's actually going to be negative 1 plus f of 2. So we'll do it this one time here. Negative 1 plus f of 2. We're going to come over here and find f of 2. F of 2 ends up being negative 2. So we have negative 1 minus 2, or negative 3. So g prime of 2 is negative 3. Then g prime of 4 is going to equal negative 1 plus a value of f of 4. So from my graph, f of 4 can be found easily. F of 4 ends up being 0. So we end up with negative 1. We could do the same two things here, plus, and then we're going to say f of 10. And finally, f of 12. Well, f of 10 is also pretty easy. That's a 0. And f of 12, it ends up being 2. So here we have negative 1 plus 0, which is negative 1. We also have negative 1 plus 2, which is going to equal 1. So there are my 4 derivative values. So we're here trying to find where g of x, it's the same as the last problem, has a local minimum. Let's recall a local minimum occurs, first of all, it's going to occur at a critical point. So a critical point is when g prime of x doesn't exist or is equal to 0. So in our problem, g prime is defined as negative 1 plus f of x. And it's clear that negative 1 plus f of x would be defined at all values of x between 0 and 14. So there's nowhere where the first derivative doesn't exist. However, there would be places where our g prime would equal 0, and that would be when f of x is equal to 1. So wherever f of x is equal to 1, those are going to be my critical value, my critical points. So when f of x is equal to 1, so it looks like right here, and looks like right there, and here, and looks like right there, and we also have a point right there. So it looks like we have that g of x does have 5 critical points. And so the next criteria to be a local minimum is at those critical points, let's check the second derivative. And if the second derivative at a critical point is positive, greater than 0, then that critical point is a local minimum. So to check if g double prime is greater than 0, that would also mean that we're going to derive, so we're going to have g double prime of x, which we can derive from my g prime of x statement, and that actually would be f prime of x. So g double prime x is going to be greater than 0 whenever the slopes of f are greater than 0, or basically when the function f is increasing. So what values of x are function increasing? Okay, we're going to have a value of x definitely here. We're increasing. And we're also increasing here. So those are two values of x in my graph. We'll call them x sub 1 and x sub 2. And I'll leave it as an exercise for you guys to find those exact values. Okay, here we have a problem that combines the fundamental theorem and the Taylor polynomial definition. We're trying to find the second degree Taylor polynomial for g of x. Remember, g of x is the same problem as it was before. And again, let's recall what that was. It was g of x is equal to negative x plus the integral function from 0 to x of f of t dt. And so, in order to find the second degree Taylor polynomial for g of x centered at x equals 4, we need g of 4. We're also going to need g prime 4. And we're also going to need g double prime 4. And that one's going to be divided by 2 factorial, or 2. And this one will multiply by x minus a, or x minus 4. And we'll have plus here. And then we'll multiply this one by x minus 4 with a quantity squared. And that's it. All we got to do is figure out what these three values are. So, in a previous video we found g of 4, but let's do it again, right? G of 4 is going to be negative 4 based on my rule for negative x, plus the integral from 0 to 4 of f of t dt. Now, the integral from 0 to 4, we can see that again, this is plus, this is a minus, those cancel, and then we end up with a triangle here of area 2, and it's below the x-axis, that's negative 2. We end up, if you recall, we ended up with this whole thing equaling a negative 6. So that's what we have. We have g of 4 as being negative 6. So my second degree Taylor polynomial starts off negative 6. And then we need the first derivative of g prime at 4. Well, g prime, recall, g prime, okay, is equal to negative 1 plus f of x. Okay, and at 4, this specifically, f of 4, we can see by the graph is 0, so we actually have a negative 1 as my value for g prime 4. So my g prime 4 being negative 1, I'm going to have a minus 1, and then times x minus 4. And then lastly, we find g double prime 4. Well, g double prime, as we saw in the last example, is just f prime. And so we have to find f prime of 4. So we need to find the slope at 4, but it's the same as the slope of the entire line. And that's just going to be up 2, all right, and then over 2. So it has a slope of 1. So my g double prime 4 is 1. So I have plus 1/2 times x minus 2, or sorry, x minus 4 quantity squared. And that's my Taylor polynomial.